This picture shows a couple of girls standing inside a metallic cage, and somebody is trying to electrocute them using lightning, and nothing seems to be happening to them. She seems happy. Why? Now, if you're thinking, hey, maybe the electricity is not much over here, maybe it's a very tiny spark, well, the same effect can be reproduced using millions of volts, lightning which is produced due to millions of volts of potential difference using what we call Tesla coils. And you can see the same effect. People inside a cage, lightning is striking that cage, but nothing happens to them. Why? Well, metallic cages are basically conductors. So let's explore how conductors deal with electric fields, and maybe we'll be able to answer this question by the end of the video. Say we have a positive charge kept somewhere in space, and close to it, we're gonna keep a spherical conductor. Imagine a metallic sphere with a hole inside of it, with a cavity inside. And let's say it's neutral. The question now is, if we are in electrostatic conditions, meaning there are no moving charges, how would the electric field change due to the presence of this conductor? We can begin by asking, why should the electric field even change because we have kept a conductor now? Well, here's the thing. Conductors have free electrons inside of them. And so if you consider a free electron somewhere over here, because there's an electric field, it's going to put a force on this electron. Because it's negative, the force would be in the opposite direction of the field direction. And as a result, this electron would start moving. But we said, hey, we want to be in electrostatic condition, which means this cannot be in electrostatic conditions. In this condition, electrons will start moving. So again, the question is, if no electrons are moving, how would the field look like? Can you pause the video at this point and try to give it a shot? Try to think about how the new field would look like. All right. So if we don't want any electrons to move, the condition is simple. There shouldn't be any electric field inside the conductor. So in electrostatic situation, the field inside the conductor must be 0. So we can go ahead and we can delete the field inside. So let me just rub this field. So the field inside must be 0. Then and only then, this electrons inside the conductor will no longer experience a force. And this is nothing special. There's nothing special about a spherical conductor. This has to be true for any conductor, which means we can now go ahead and write a general conclusion. In electrostatic conditions, electric field inside any conductor must be 0. But you could ask, well, what exactly is happening? What's happening to that electric field? And well, here's how I like to think about it. We've already seen these electrons are gonna, when there was a field over here, the electrons start migrating towards the positive charge. And as a result, they end up coming somewhere over here. They can't move outside the conductor because it's an insulator. Imagine it's vacuum. So they will all get migrated somewhere over here. So all our negative charge will get accumulated over here. And because this is a neutral conductor, if the negative charge gets accumulated over here, it must have left a positive charge somewhere. And wherever there's a positive charge, more electrons would just keep accumulating. Eventually, there will be a positive charge somewhere on the outer surface of this conductor, somewhere like this, so that the total charge on the conductor must still be 0. Charge conservation. We cannot create or destroy charges. And because of this positive and negative separation, they are now going to start producing their own field. They're going to start producing a field inside. Let me use a different color for that. Let's say I'm going to use blue to represent the field that they have generated. So they might generate a positive and negative field that would look like this. And guess what? This field, the internal field, exactly matches and cancels with the external field. And because of that, the total field goes to 0. Now you may ask, how do you know that it exactly matches? Well, it has to. Because if it didn't exactly match and it didn't go to 0, electrons would still be moving. So think of it this way. The electrons will keep moving until the electric field generated inside matches and cancels out with the electric field from the outside, making sure that the net electric field inside the conductor has to be 0. Beautiful, right? So is this how our electric field is going to look like? No, not really. We're still not done yet, and things are going to get more interesting now. Now think about this. Because electric field everywhere is 0, this means that our entire conductor must be an equipotential surface, meaning that every single point on the surface or inside the surface, inside the conductor, should have the exact same potential. Now, again, I want you to pause the video and think a little bit about why should this be the case? Why, if we say electric field is 0, it should be an equipotential surface? Can you try and make that link yourself? All right, here's how I like to think about it. Consider any 2 points on this conductor. Maybe say one point inside over here, maybe another point inside the cavity somewhere over here. Now imagine you have to take a charge from point A to point B. In doing so, how much work would you do? Well, think about it. There is no electric field inside. If there's no electric field inside, you don't have to do any work against the electric field, which means you do 0 work. And that should be true for any 2 points. So let me write that down. This means the work done in moving any charge between any 2 random points A and B should be 0. In other words, potential at A must be exactly equal to potential at B. And A and B can be any 2 points on the surface, inside the cavity, any 2 points, because there are no electric fields. And what does that mean? That means the potential everywhere must be the same, meaning our entire conductor is an equipotential surface. So another interesting thing we see is that in electrostatic conditions, conductors, the entire conductor must be an equipotential. Again, nothing special about spherical conductors over here. All conductors should obey this rule. But you may ask, okay, how does that affect our electric field? Well, remember one property of an equipotential surface? These surfaces must always be perpendicular to electric field. And if you're wondering why should this be the case, we've spoken about this in great detail in a previous video on equipotential surfaces. So feel free to go back and check that out. But here's the thing. Over here, if you look now, this means that all these field lines which are touching our conductor must be perpendicular to the surface, and they're not. Over here also notice they're not perpendicular. This angle, these are not perpendicular. So somehow the field lines must change, must bend to ensure this is true everywhere on the surface. So again, can you pause the video now for one last time and think about, try to draw a sketch of what this would look like. All right, here we go. So the field lines must bend in such a way as to they are perpendicular at every point they are meeting the conductor. And so if you look at this, this means that this conductor is sort of like sucking the electric field. And that's why even these field lines are gonna sort of like bend towards our conductor, because they're gonna sort of like getting sucked. Now look at how complicated this situation has quickly gotten. But we now understand that. We understand why this has to be true, because it's an equipotential surface, because of some basic rules that we had learned earlier. Now let's see if we can answer our original question. Imagine this field was incredibly strong and there was air over here. In such cases, you can get lightning. And we'll talk more about how that happens and all that fun stuff in the future videos. But let's say there is this lightning strike happens. Now where will that lightning go? Can it enter inside the conductor? Well, remember, lightning is basically charges moving in an electric field. Now, if there is no electric field inside a conductor, the charges will not move inside the conductor. So what will happen is that these electrons or these charges will find a way to go through the surface and eventually somehow go into the ground. This means if there was somebody standing inside the conductor, and let's say she was touching the inner surface, she will not be electrocuted by that lightning. Now here it doesn't look so dramatic because it's a thick conductor, but the same thing would work even if it was an incredibly thin conductor. And that's exactly what's happening over here. This is a closed conductor. Electric fields cannot penetrate inside this conductor, because of which when she's touching the inner surface, the lightning cannot enter the surface, and that's why she's not getting electrocuted. This effect is called electrostatic shielding, because as we can see that the inner surface is shielded from the outer electrostatics. And this was first discovered by Michael Faraday. And so a closed metallic conductor is often also called a Faraday cage. So we would say that these girls are standing inside a Faraday cage, which is shielding them from the outside electrostatics, and that's why they're not getting electrocuted. This is also the reason why airplanes can get struck by lightning and nothing will happen to the inside, because the entire aeroplane is a metallic body. It acts like a Faraday cage, and therefore lightning will not penetrate. And in most cases, even when the lightning strikes an aeroplane, it doesn't do any damage.